I would like to explain to you how we managed to fit a 1 megabyte demo, which was from a 16-bit machine into an 8-bit BBC Micro with 48K of RAM. This wasn't just me. I had a lot of help from many people, particularly Tom Seddon, Simon Morris, John Blythe, and Dave Newman, who was our amazing musician. Come on. Slide. There we go. Right. So yeah, what is the demo? You now know because you've seen it, which is great. But this was originally an Atari STE demo, actually, from back in 2000, and it was sort of at the time regarded as this amazing demo for the ST, and the likes of which nobody had seen before. But the data format for the demo was actually reverse engineered a few years ago, and it turns out to be fairly simple. And it's become one of those kind of challenges, like can you port it to other platforms? And there was actually a competition in, I think it was November 2018, to see how many different platforms people could port the demo to by Easter 2019. And so we were kind of late for that, but there were quite a few different versions that have existed. There's only one 8-bit version, and that's for the Atari 8-bit, but it uses this BEEB NICCC, which I'm not familiar with, but apparently it has a blitter in it, which is kind of cheating. So, you know, all of these things always start with a challenge and a sort of question. So could this be done on a BBC Micro, or could we do it properly? Because I'm all about making things that could have been done on original hardware back in the day. Maybe we just didn't have the time or the perhaps some of the modern tools to help with that, but everything has to run on original kind of stock hardware. So this is the Polygon stream format. I should have said up front, this is going to be a technical talk, quite a change of pace from what Mike's just shown you. So I hope you all like assembler. Hopefully you'll also get something from it. But the data format's fairly simple. Every frame has a flag which indicates what's in the frame. It's got some optional palette data, which we haven't really got time to talk about. But essentially there's a set of vertex data and polygon data. And there's two different ways it's encoded. It's either encoded in a sort of indexed format, or it's just there is a polygon with a description and then a set of XY vertices for each corner of the polygon. And so it's a fairly simple stream. So the first thing I did was just write a quick parser in Python just to look through the stream and try and get some stats from it, just to try and get an idea of whether this might be possible. So there are 1,800 frames in total for the animation. So it's a 625K data file. And so this is about 355 bytes a frame. The original demo runs at 10 frames a second, so you kind of go, well, it's 3.5K a second. I know from the Bad Apple demo that we could stream 4K a second off a floppy disk, so yeah, maybe this could work. The whole demo has 75,000 polygons. There's an average of about 40 polygons a frame. Okay, that's pretty high for a BEEB. The highest one actually is 164 polygons on, I think, the very first frame, which is obviously a lot. The polygons themselves are not triangles. They can be up to 7-sided, but they typically end up being 4 sides, so quadrilaterals. And yeah, there's quite a lot of edges. So yeah, there's 300,000 edges to draw across the entire sequence. And then spans, so the number of horizontal lines that you would need to fill in those triangles. Turns out there's 3 million across the entire sequence. So the average sort of screen height of a polygon is 40 lines, so 40 spans per polygon. And so yeah, there's quite a lot to do. But anyway, it's good to have the numbers. The data is sort of quite nicely pre-formatted. So everything's already in 2D. There's no even though it's a 3D demo, there's no 3D maths to do. It's already pre-sorted and clipped into 2D, and it's rendered at Atari ST resolution, so 256 by 200, 16 colors, and all the polygons are convex. So that means we can use a span filling polygon routine. So for those of you who don't know how that works, I'll go very quickly through this. So essentially, you can use Bresnan's line algorithm to draw edges, but instead of drawing the edges in wireframe, you essentially just draw the coordinates into a table. So say we want to draw a polygon here, rather than plotting pixels to the screen, we just record what's the minimum X value and the maximum X value on each line. So we go around, fill in the table, and then as you start to enclose the polygon, you overwrite those maximum X values on the side until you've completed. So we have this table now of the spans that go across the screen that would make up our polygon. And then in theory, all we need to do is just draw pixels between the minimum X and the maximum X on each line. And we end up with, in this case, a very crude approximation to our 5-sided polygon. So I already had a Breslin line algorithm. I actually stole it from Rich Tolbert-Watkins. It's the one that's on the retro software site of old, and it's the one that I always use as a starting point for everything. So now I just need a routine to plot spans of pixels. I had a lot of sort of thoughts about which mode this should be in, but really for a BBC, like mode 5 is the only sort of viable mode really for this demo, unless we wanted it to be black and white, which I did contemplate, but I wanted it to have some sort of color. I should stress the newer version that you saw at the beginning is actually in mode 8, technically, which we can talk about at the end if we have time. But the original demo needs to be in mode 5, so we've got some colors. Can't afford mode 2. There's no way we can have enough memory to double buffer it on a regular BBC, but also just the amount of time it would take to fill that much memory. So this is in mode 5, but reduced. It shrunk down to 128 pixels across and 200 pixels down. So that's 32 columns, 25 character rows. So we can double buffer that in 13.5K, which isn't too bad. So if this is sort of one line of our mode 5 screen, we've got 32 columns here, 128 pixels. And of course, it's 4 pixels per byte. So say we want to draw a nice long span of pixels. Maybe we've got something that goes from X, on the left at 6, and it goes all the way to 120. So we've got 115 pixels that we want to plot on the screen. Well, because of the 4 pixels per byte, it's slightly annoying, right? We've got to start by masking in 2 pixels at the start of the line because you don't know what's on the screen already. Then we can write a load of consecutive bytes nice and quickly, and then you've got to mask in your pixels again at the end. But this isn't too bad, right? We can use some tables to do the masking for the start and the end, and then just a simple loop to write some consecutive pixels in the middle. So I've got my Breslin line algorithm, I've got my pixel span, so it's time to get something drawing on the BBC. So step 1, just take the first 64K of data, put it into the BBC Master's sideways RAM and pass it from that data format and draw it. Simple, right? And actually, it turned out to be okay. There's some errors here. This is a screenshot from the very first check-in that I had in my GitHub repo. So you can see it did actually work after some initial problems, just making sure ironing out the bugs in the various routines. But that's pretty good. That looks okay for a first attempt. But obviously, we're not going to be able to load it. It's going to be pretty rubbish if we just load 64K chunks at a time. So we need to stream the data. Thankfully, I'd already done a streaming demo, which was Bad Apple demo, which you might remember from a few years ago. And so I can lift the streaming code from that, and hopefully it'll just work. So the streaming uses Osword 7F. So that loads a track at a time. So you load 10 sectors, 2.5K. We've got 3 tracks, circular buffer. So we've got 7.5K of buffers for loading in the data. Anyone that's used Osword 7F knows that Osword 7F is a blocking call. And so it doesn't return until it's finished loading everything. And this means you can't do anything else at the same time unless you put it in some sort of IRQ handler. So that means we have to move everything. So all of the parsing, all of the plotting, all of the music and everything else all has to run from an IRQ handler. But of course, I'm sure you've read the Advanced User Guide, for those of you that program such things, and it does advise, I can't remember how many milliseconds, I think it advises you return from your IRQ in 2 milliseconds. Well, some of these frames, they can take sort of 10 or more VSyncs, so you're looking at, what's that? That's many, many milliseconds. And so we have to re-enable interrupts whilst we're inside our IRQ, which means that the interrupts themselves are, interrupt handlers are re-entrant. Yeah, this can get a little bit icky and quite messy, so handle with care, but it is possible. So now it's up and running, but it's very, very slow. I think the first version that I had was about 2.5 frames a second, and so we want to optimize this. And first thing I did actually was to come up with 3 different quality levels. So this was the original sort of high quality, which is sort of full mode 5 resolution. And then this is medium quality, where actually we only draw every other line, and then we just double up the scan lines in between. And then there's this low quality version, as I called it, where actually we're just skipping scan lines. And you can see there's the same dither pattern there, but in the middle they're doubled up, and on the left-hand side, there's a blank line in between each one. And actually I kept these versions running for quite a long time because I sort of held out that I would hopefully optimize it enough to have the highest quality version. But in the end, we ended up on the left-hand side for the final demo for reasons that I'll go into. But the nice thing about this is that you can measure everything. Everything's measured in vsyncs. So if you run the entire demo from start to finish and you get a counter at the end for the number of vsyncs, and you make a change and then you measure and you see what the new vsync count is, and if it's smaller, then you've optimized it. And sometimes, quite often, you make a change and it actually gets larger and you've made it slower. And so you have to measure everything. You can't make any assumptions. The nice thing here is that, you know, at this scale, just saving a single cycle in the plot span routine, because it's called 3 million times across the entire sequence, saves 75 vsyncs. So that's 1.5 seconds saved across the entire sequence from saving a single cycle of assembler. What was also quite surprising and why we had to test, you'd think that you could kind of come up with different code paths for kind of different kind of optimal situations on screen, but actually quite often, because you're calling these functions so frequently, the amount of time it takes to detect that different code path and jump to it is actually slower than just having some sort of average case routine instead. The one thing we did do though is we use lookup tables to optimize as much as possible. So we use lookup tables for masks for short spans of pixels. So anything up to 13 pixels wide, you only need 4 bytes to draw that on screen. So you can store all combinations of 13, between 1 and 13 pixels shifted for the 4 pixels in a byte. So you store all 4 possible offsets, and then you just need to pick the right set of masks, and you can just draw those directly to the screen. So that's only 208 bytes. I think we can afford that as a lookup table. That's not too bad. As with everything on 6502, if you want to make it as fast as possible, then you need to unroll everything that you can and try and avoid loops if you can afford it. So if we wanted to think about our imaginary like perfect line drawing routine, we're trying to draw a consecutive load of pixels on the screen as fast as humanly possible. Then the optimal sequence would just be a load of store absolutes, right? So a line might just be store, 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 and we kind of perfectly know how many of those we want to execute in a row, and then that would end up being 4 cycles for each byte. It's 4 pixels in a byte, and so we get 1 cycle per pixel. That's kind of our theoretical optimal maximum. But if we were to do that, we would need to unroll all 200 scan lines with 32 store instructions, and that would be about 19K of unrolled code, which doesn't sound very feasible. Although I guess you could do with sideways RAM. But actually it's worse than that, because we're double buffered, so we need the addresses of both screens. And so yeah, that would be a lot of memory for code. So Tom Seddon came up with a great idea. So rather than using just store absolute, we use absolute index with Y instead, and we unroll just the character rows and make the Y index work extra hard to index where we want to within a character row. So we've got 25 character rows, 32 columns. Yeah, that's about 2K of code. That's not too bad. Of course, it's double buffered, but 4K. Yeah, I think we can squeeze in 4K of unrolled code. That's not too painful. So this is probably the most technical slide of the whole presentation. Here's an example of one of our screens, row 24. We've got all 32 of our store instructions pointing into memory. And so we need to, first of all, if we're trying to plot a line, we need to calculate which character row we're in. Well, that's easy, we know that. We just divide by 8. We have a lookup table to work out the address of this function, this unrolled code. We're going to make Y work extra hard. We're going to make Y be both the character column and also the scan line offset within that character row that we want to draw. This is actually just our X position in times 8, because we know that we have to move by 8 bytes for each byte as we move along the screen, and our Y position modulo 8. And then we use another cunning lookup table to work out where we need to jump into this function in order to plot the correct number of bytes. If we want to plot 32 bytes in a row, then we start at the top of the function. And if we want to plot just 1 byte, then we start at the very bottom of the function. And then we just jump into the routine at that point, and you can see it actually runs backwards, that routine, so you end up with the correct number of bytes at the starting point that you need, offset by y. And so this is 5 cycles per byte that we're plotting. There is some fixed overhead, but this comes out at about 1.6 cycles per byte for the very longest spans, which is actually pretty good, I think, for what we're trying to achieve. And yeah, win. There's lots of other 652 optimizations that we spent time doing. As I say, this is a sort of painful routine of just trying something, tweaking it, and just running over and over again to see what the numbers come out like. But some things that I found really useful, I've got macro in BEEBasm, which checks whether any branches cross a page boundary. And again, for the loops that you do have, if you cross a page boundary, then you incur another cycle penalty. So you want to make sure all of your code is aligned within a page wherever possible. Another macro to check that tables themselves don't overspill page boundaries. You can't have every table page aligned, but for smaller tables, just making sure they don't ever accidentally skip into the next page is really helpful. Inline whatever you can, if you can avoid having to jump to other functions, but just put that code directly inside another loop or inside another function, then that's really helpful. But again, beyond a certain size, you're breaking your ability to branch, and so you can't always do that. So instead, this was a really helpful trick. Rather than using jump to subroutines, so JSR and RTS, now that's 12 cycles overhead, 6 for each. If you know which function you're going to and you know where to come back to, then just use jump instead. Right? There's no need to push the return address on the stack. You can just jump directly back to where you came from by just hard coding that address. Yeah, up until this point, everything had been tested on emulators, and so it's like, I should probably test this on real hardware and make sure the emulators are accurate. And actually, it turns out that modern emulators, so certainly the emulators written in the last couple of years, are cycle accurate on the hardware side. What is interesting is that I don't believe anybody accurately emulates kind of floppy disk behavior, and certainly different emulators sort of approach things like seek times and read times differently. But it turns out they're kind of good enough. The numbers came out basically pretty close, certainly within a second or two across an entire 3-minute sequence. So they're certainly accurate enough for our purposes. But yeah, definitely worth checking. At some point, you've got to try these things on real hardware. And then the final thing that I did, which is probably the first thing you would normally do, is just reduce the amount of work to do. I did get us up to over 5 frames a second at the lowest quality setting, but this would make the demo 6 minutes long, so that wouldn't actually be fun. And I'd spent a lot of time kind of wrestling with what to do about this, because the original competition was to use the original data sort of untouched. And I kind of figured, well, we've proven it is possible to do that on a BBC Micro, but it's not a demo, it's not going to be entertaining. And so I actually repassed all of the data and reduced the sequence to 900 frames. So just took every other frame out of the sequence. And this brings the demo down to 3 minutes, which is much more palatable. And it also meant there were some other opportunities to make some small savings. And it also meant that we could align all of the data to our circular buffer that we're loading into. So it means that you never have to worry about wrapping around the data pointer when you're passing the stream. Yeah. And the other bonus, the whole thing now fits on 1 disk. So rather than having to have a 2-disk demo, the data file was 320K. We can fit that on a 80-track disk, double-sided 80-track disk. So yeah, this is also much more convenient for our purposes. And yeah, so that's a real whistle-stop tour of everything that we did to make the 3D demo work. But that's about 50% of everything that we had to do to make it into something we could actually release. There's still music needed. There's the intro that you saw. There's the outro that you saw. There's lots and lots of attention to detail that goes into polishing the demo and making it look and feel as smooth as possible. Try and remove any glitches, and lots of testing, particularly on different types of hardware, different devices. And yeah, deadlines help with this. It really helps you focus on what's important. And we were aiming to release at the revision party. So that's the biggest demo party in the world. It's held in Saarbrücken in Germany each year. But of course, this year it was all online. And we submitted that for the old school demo compo, as they call it, and won. So it's the first time a BBC has been entered into revision. And yeah, many of the people at revision didn't know what a BBC Micro was. But now they do, and yeah, so we've put the BBC on the demo scene map, and yeah, we hopefully will be able to attend in person next year and have something bigger and better. And then you saw the NULA version, so that's cool. Again, big thanks to Tom Seddon for making that happen. And I think, yeah, that's it. Wow, that was quick. But yeah, I'm happy to answer any questions. This is the this is what it looks like if you don't have a NULA. But yeah, and big thanks to everybody else that helped out and chipped in with support and suggestions, all listed here.
Yes, thanks for sharing that, Kieran. It's incredible. I've got a techie question around the disk access, and you're saying, you know, you're enabling interrupts within an interrupt. So when you are reading disk, do you have to, with that setup, do you have to wait for the OS routine to complete so it does fetch the full? Fetches a, well, I guess it has to fetch a full track, and then you carry on. And given that, well, how do you manage to avoid you know, stutter or delay in the rest of the routines that you're running?
It's a very painful sort of balancing act, really. Yes, it's a painful balancing act. So you load the data into the ring buffer, and you're consuming it in an interrupt at the same time, and there's no real sort of check as such to stop you from running out of data. So it's you can sort of detect and keep an eye on the pointer that you've got going through your buffer as you're reading it, but you don't really know where the data is currently being written to by the disk routine. And so it's more kind of trial and error of making sure that you get your buffer sizes right, so that you've got enough space that you don't sort of catch your own tail. Yeah, and it's kind of different for every demo. I can't remember what the sizes were for Bad Apple, but we were consuming data at a different rate for Bad Apple. But yeah, it's kind of lucky, I guess, that the data rate sort of matched up with the BBC sort of DFS speed, which is about 4K. I think theoretically you can get a bit more than that, but certainly sort of in my empirical tests, if you're running everything else on the machine at the same time, because of course you've got NMIs that are doing all of the copies to put the data in RAM, and so they're firing all the time, plus your interrupts. Yeah, there's a lot going on, and it sort of relies very heavily on the interrupt system working, and you also not blocking your own interrupts. Right? If you spend too long in the interrupt handler, then your interrupt flags are just backing up behind and not getting serviced. So hence having to re-enable them when you're doing any sort of significant work. But then also check when you come back into the handler which ones you do want to service, and then which ones you want to ignore again.
Okay, thanks.
Can I ask a question, please?
Of course.
Amazing for a start. Going back to your early slides, the table that you build up with the Bresenham's algorithm, do you do that once for each polygon, or do you do it once for the whole screen?
So that's once for each polygon.
Wow. And so that table could be up to a screen height, I guess, could it?
Yes. Yeah. So that's where it can get very expensive and very slow. Yeah, it's that just keeps the algorithm simpler, because you're only ever having to plot sort of one span. Otherwise, you'd have to have all sorts of bookkeeping if you can have multiple spans per scan line. But yes, in theory, again, you could build all that up and then just kind of go over the screen and just plot all the little spans. But I think you'd find, certainly in the 6502, the amount of bookkeeping to kind of keep all that data, particularly sort of arbitrary lists of spans on each scan line. You sort of end up in some sort of linked list hell, which isn't going to be 6502 friendly.
Yeah, I mean, I, as you say, it's cheating, but I've been doing the blitter thing, and I've just started to try and get my head around the triangle plotting, and that sort of blew my mind. But this sounds like a really cool way of doing it. So are you okay for me to like nick your code and have a play with it?
Yeah, of course. Yeah, it's all in GitHub. Yeah, it's not necessarily the fastest way to plot triangles, but it's certainly, just because this demo is, say, you can have up to 7-sided polygons. It's kind of it's sort of the most general purpose, I suppose, polygon plotting routine. But you can have sort of faster triangle plotting routines.
Yeah, but this actually looks like a better idea than the triangle, and I suppose the triangle will be a sort of degenerated case of this. So no, it's amazing. I'm really impressed.
Thank you. Any more questions?
Actually, sorry, I'll ask another one if nobody else is wondering.
Yeah,
with a music player, I'm guessing that's VSync-ish sort of speed, is it, or is it?
Yeah. It has to be polled at 50 hertz. Yeah.
Wow. So how do you fit that in between? I'm guessing, have you got separate timers for the code, and then the music player interrupts the other code?
Yes. which is why you notice if because if the music comes in late, if you don't service that interrupt because you're busy doing something else and it comes in too late, then it gets you can really hear it. Like the music slows down or it stutters. As I say, it's one of those things. I don't think I would have been able to do this if I hadn't done Bad Apple first, because we kind of experimented and learned a lot about sort of re-entrant interrupt handlers and this kind of way of doing streaming. Turns out, actually, Scary Beast, who's not on yet, I don't think, but when he comes on later, he has some cunning plans for how we might be able to do non-blocking streaming by writing our own lower layer disk handling routines, which could be really interesting, actually, and might enable us to do other things. But watch this space.